Welcome to our part 2 of revision questions in modern algebra. In our previous video, we did question 1 to question 16, and today we begin from question 17, and that marks our beginning of part 2 of revision questions. So you should be having a calculator because we'll require it from this very start to the end. Thank you. So now I want to use the inverse to solve equations. We've done this equation before, but we use the Euclid's algorithm. But this time we want to bring in the inverse a bit, but of course we still use the Euclid's algorithm and then find the inverse. Multiply by the inverse of both sides. Now, so we want the inverse of 15. Want the inverse of 15, then multiply by that inverse on both sides. So I want to do it slightly different from the way I did this question before. Begin by finding the inverse. If you know it, then you can just multiply on both sides. But for this one, I don't know, so I try to work out. Suppose I don't know, I take that too. I ask myself, 15 goes there one time, 15 goes there twice, and the remainder is 2. What about 2 into 15? The remainder will be 1. And then 1 into 2, and the remainder will be extra reverse. Then I reverse, and make 1 the subject of the formula because it's the GCD. And this will be 15 minus 7 multiplied by 2, which is 115 minus 7. Instead of 2, we write that 2 minus 2 raised to 2. Collect like terms. We begin by removing this bracket, minus 7. That's 2. Minus 7 times that will be positive 14. Positive 14 plus that will be positive 15. So in other words, the inverse of 15 is. So what we were doing earlier is that we would then multiply, because we were 1, we were just multiplying this expression by 7 and read the value that will be here. We're just multiplying this by 7 and read the value that. But this is not what I want to do. What I want to do is that after I've found this inverse, I now multiply this equation. Let me call it x star. Multiply star by the inverse on both sides. Not that. Star by 10. Because 15 is the inverse. When I multiply 15 on the left side, and this side also multiply by 15, this first bit gives me 1. Times x will be x. And this other one, the 15 times 7, this is my calculator. 15 times 7, I get 105. How many times does that 2 go into 105? That 2 goes there 3 times. So what is the remainder? That 2 into 105, what is the remainder? The remainder is 9. So that is the value of x. That's the value of x. 9 is the value of x. That is how we do it using the inverse. But the other one, we were just multiplying it here and reading the value here. We would still have gotten the same thing because when we multiply by 7, this equation, this will have been 7. This will have been negative 9. But this will have been 7 times 15, which we found to be 9. Now solve for x. Solve for x. So the question is, can I find x? I still want to use the inverse. Let me find the inverse. First find the inverse of 5 more than 12. So what is 12? 5 will go there twice. 5 to go there twice and the remainder of the cube. What about 2 into 5? The remainder of the 1. What about 1 into 2? The remainder of the 0. So now 1 is precisely and the reverse. Reverse. Begin with this question. Make 1 the subject. 1 is 1 multiplied by 5 minus 2 multiplied by 2, which is 1 multiplied by 5 minus 2. But instead of 2, we write this. This will be 12 minus 2 multiplied by 5 minus 2 multiplied by 5. So when we do this, first of all, let me do that. I have negative 2 multiplied by 12. And then negative 2 multiplied by negative 2 will be positive 4. Positive 4 plus this one will be positive 5. So I've found that the inverse of 5 more than 12 is 5. So multiply by this inverse on both sides of this equation. Let me call it a star or a double star. So multiply double star by 5. When I do that, I'll have 5 times 5x is congruent to 5 times 4 more to 12. And the first bit is 1 times x, which is x. This is 20 more to 12. But 20 is bigger than 12, so I reduce it more to 12 to 28. So, and again, we know that this is the remainder. It's 12 for 20. And so that is how we do this question 18. I want us to proceed and do another question. But first of all, let me clear this. Let us now look at this question 19. It is this question is just the same as find the inverse of 15 mod 26. We will do these questions. But let's just do it. We use so we want to find 15x. We want to find an x there, only x, such that give us this remainder of 1. I want to find an x such that x times 15 divided by 26 give us a remainder. That's all. So using Euclid's algorithm. We have 26. 15 goes there once. And the remainder is what? Remainder is 11. What about 11 into 15? The remainder will be 4. What about 4 into 11? 4 into 11. The remainder is 3. What about 3 into 4? 3 into 4, the remainder will be 1. What about 1 into 3? And the remainder is 0. So this is our GC. So we make it the subject and we work it going up. So 1 is the same as 4, 1 multiplied by 3, which is 4 minus 1. Instead of 3, we are writing 11 times 2 multiplied by 4, which is 4. This is 1. Let me work out this one first. Negative 1 into 11. Then this is negative 2, and there's positive 2. Negative and negative, positive 2, and there's a positive 1 there. That is 3, 4. And so, negative 1, 11, but instead of this 4, 4 is here. So I've got 15 minus 1. So this, let me work out the bracket first of all, which gives me 315 minus, there's a 3 here, minus 3, and there's a minus 1. So let me just combine. Minus 3, minus 1, talking minus 4, 11. So now, instead of this 11, I know what it is. I know that 11 is here. It can be replaced by this 2, which is 26. It's 150. And let me just continue from here. And this gives me, let me work out this bracket. Negative 4, 26. This is positive 4. And there's a positive 3 here, which together mean positive 7. Multiplied by 15. The question wanted me to find a value that is multiplied by between 1. And that value is 7. So the inverse of 15 more than 6 is 7. You can do the same thing, for this question too. Same thinking, but let me just do it. I can even do it using the other method we did earlier. This is 5x is congruent to 12 more than 4. That is what the question is saying. I can use the earlier method, and I just want to find the BCD of this. For that BCD exists, it's 1 divides 12. So there's a solution, only one solution. It's only one solution for this. So by Euclid's, and I know that at the end of this you have understood this whole concept because you're doing the same way it's every time. So 44. 5 will go there 8 times, and the remainder. And 4 into 5, of course, it will be 1. And then 4, 1 will go there 4 times, of course, and the remainder. So now just note that the 1 there is the BCD. So we now reverse. 1 is the BCD, and it's the same as 5 minus 1, 4, which is 5 minus 1. But instead of 4, we are writing 44 minus 8, 5. And so what is this? Negative 1, 44. And this will be positive 8 plus 1, which will be positive 9. And then, so what do we have? We have 1 is equivalent to negative 1, 44 plus 9, 5. So 1 is the remainder, but we want the remainder to be 12. So multiply this star by 5. Multiply star by 5. When that happens, no, by 12. Because 12 is the remainder here. To make this remainder also be 12. That 12 is congruent to negative 12 for 4 plus 12 times 9, 5. And we are doing modified 44. I'm only interested in this part because this will give me what must be multiplied by 5, the x, the x. So that's what I'm interested in. So x therefore is 108 mod 44. I think it's 108 12 times 9. So now I just want to find what will be the remainder when 44 goes into 108? Because there are 12 times. The 108, no, because there are twice. Because there are twice. The 12 times twice. And the remainder will be good. The remainder will be good. And that is what we wanted. So after that, we have good questions, and I've included answers so that you can try and find the same results. Just wanted to see whether you now find inverses, reminders, and so on. But just using the examples, we can do it. Let me now come to some questions here. This question says tick true or false. Just get a point, tick true or false. Says A. If A divides A square, then no, if 9 divides A square, then 9 divides A. You know that vertical line means divides. If it's not the same, it's not slanted. Slanted means something different. This also means something different. But I'm using this vertical line. That's not this. Okay, so if the next if 9 divides A square and then 9 divides A, is it true or false? Is it true or false? Let me see. I want to take an example of 9 divides 6 square. That one I know because 6 squares that's 6. 9 divides that's 6. But can the same 9 divide 6? Cannot. That cannot divide 6. But this is false. This is false. I've just taken an example. To show that it's false. I know that 9 can divide it at 6, which is 6 square, but we cannot divide 6. So this statement is false. What about this? If D divides A and D divides B, then it divides the BCD of A and B. And this is true. This is true. You can take any number. You can take even 2 divided 6. And so that our D is 2, and 2 also divides 8, and that our B is 8, and A is 6. And you can see that 2 would also divide the BCD of 6 and 8, which is still 2. Which is still 2. Or the GCD of 6 and 8. 6 and 8. 3 goes at 3, 3 goes at 4. So this statement here is correct. This statement here is correct that if a number D divides A and then D divides another number B, then that D will divide the GCD of these two numbers. What about this one? See, let me see. Let's one just take an example. What is 2 raised to 4 minus 1? 2 raised to 4 minus 1 is equal to 2 raised to 3, which is 8. Which is 8. But 8, I can see, is not congruent with 1 mod n, and n in this case is 4. N in my case is 4, because it's 2 raised to n minus 1. So I've taken my n to be 4. I know that this would be 0, and 0 is not congruent with 1. But now, what I don't like is this part. They say that if this is the case, then n must be prime. But I can see that n here is not prime. I can see that this n is not prime. So it means that this statement is yes. Now, what about this? The linear congruence, this equation has 5 solutions. Is that true? For us to know the number of solutions for this congruence, we need to get a GCD of that 5 and see where that GCD divides it. If that GCD is 5, then it will have 5 solutions. Let's see. That 5, 150. 5 goes here further. 5 goes here 30. And there is not a number that can divide this. So 2, the GCD is 5. And 5 can divide this. So this congruence has a solution. And how many solutions? 5 solutions. So this statement is true. This statement here is true. What about this? That if 15 goes into negative 93, the remainder of the group, let's see what it's 15 into negative 93. This one requires a calculator. 93 divided by 10 goes down negative 7 times. Remember, I said I pick the one higher. So 7 times 15, that would give me 105. When I subtract 93 negative 3 plus 105, because it's minus, plus, that gives me 12. The remainder here is supposed to be 12. Not 3. In fact, anything that's red, it may be negative 3 will have been correct. If it will have been negative 3, it will have been correct. But if it has to be positive, then it must be correct. But if it has to be negative, let it be negative. So this statement is correct. If A divides M and B divides M, then AB divides M. Let me see. Let me take my M to be 12. Let me see. And A, let me take it to be 2, and B be 3. So that 2 divides 12, and 3 divides 12. That's what the question is saying. A divides M, and B divides M. Then what about the product? 6. It will divide 12 plus 4. And this will work for any other numbers. So this statement is correct. That statement is correct. What about this? If the GCD of this is 3, then N and M are relatively different. The word relatively prime means that they have the only common factor is 1 between M and N. So it's saying that if the GCD of these two numbers, let me see, 3 times 7, for example, times 3 times 9. That's what it's saying. So that the GCD is 3. The GCD is 3. But this is true. That if the GCD of this product is 3, then these other numbers are relatively prime. 7 and 9 have only 1 as a common factor. But if they had another common factor, then 3 ceases being a GCD. The GCD becomes something different. For instance, if this was to be 8 and this was to be 6, so that there's another common factor, then the GCD of this will not be 3, it will be 6. The GCD will be 6. So that would have factor these two out, and I would have 6 followed by 4. Then this other one factor 2 out, 6 followed by 4. So again, so that GCD will be 6, and remember this again remains together with 5. This other remains together. So once you factor the GCD out, what is left must be relative to 5. Now, so I want to show something different. The use of Chinese remainder theorem, and I hope this concept now is what will bring our exercise to revision questions to the end down to the Chinese. So these are simultaneous congruence questions that we want to solve. So I want to assume that this is my question 1 and that this is question 2. And so using question 1, what does this mean? First of all, what it means is that if 5 were to divide x, we would get some value t and then the remainder of 2. So in other words, x can be written as 5t plus the remainder. So that is why I said using 1, we have that x is the same as 5t plus 2 for some integer 2, not some integer t, Now, so I substitute this equation 3 in 2. Substitute 3 in 2. While there is x, just write this. So what do we have? We have 5t plus 2 giving us 3 mod 7. So take to the other side of the subject of the equation of the equal sign, that gives us 1 mod 7. So what is t? And we've been solving this kind of equations, finding t. So look for the inverse of 5, for instance, or use this algorithm. So you have so many choices of how to do it. The inverse of t, I see it to be 3. So that 3 times 5, 10 times 5, divided by 7, the remainder will be 1. So 5 inverse. So multiply this, multiply star by 3. So we get to be 3 times 5t is 3 times 1 mod 7. And this gives me 1. And this gives me 3 mod 7. So t is 3. So go back to question 3 where there was t and find x. Using question 3, using question 3, we have this substitute t, we have x as 5t, is t, 5t plus 2, which is 15, 17 mod. Now the mod becomes the product of these two mods. It is that. That is the value of x. That is the value of x 17. So you notice that if x is 17 divided by 5, the remainder will be 2. If x is 17 divided by 3, now divided by 7, the remainder will be 3. That is that x is that 17. I want to take another example to make this clear. Now for this question, it's slightly different from the one we've had because the one we had had an x and an x, but this one has 2x and then 3x. That means we must multiply one of the equations or even the two equations by the inverse of 2 here, and then this one multiplied by the inverse of 3, or you can just do one of them. Let me do the first one. Let me call it this one equation 1 and this one equation 2, and find. So I'm using 1. I'm using equation 1. Using equation 1, find 2 inverse mod 7. So I'm looking for a number which will multiply by 7, multiply by 2, and then divided by 7. The remainder will be 1, and that number is 4. Because 2 times 4 will be 8. Divided by 7, I get 1. You can use the Excel to record, but this is small, is very small. You can see what the number is. Okay. Now, so then multiply equation 1. Multiply equation 1 by 4. Yes. So 4 times 2x, 4 times 5, 7. So what you get, this is 1 times x. This is going to 20 mod 7. 20 mod 7. If 7 was going to 20, you get 14 somewhere in the remainder 6. So that twice the remainder of 6. Now I want to call this equation 3. But what does equation 3 imply? But equation 3 implies that x is the same as 7a plus 6 for some integer a. So what I mean, this equation means that if 7 divides x, the remainder will be 6. You get something, I'm calling it a. If 7 divides x, you get something I'm calling a, and the remainder of the 6. That's what I've just put. So this is what I now substitute equation 2. Substitute equation. Substitute equation. Yes. Substitution 2 get 3. X is 7 plus 6. Then it's congruent to 4. Now the 8. So what I just need to remember, I need to remember this equation. Because this is where I'll come back. After getting a, I'll come back and x. So then, let me create some space here. Create some space here so that I can work the rest of the question. Now, so let me just open the brackets here. 21a plus 18 is congruent to 4 by 8. Let me take 18 the other side. 21a congruent to 14 now the 8. Yeah, that is mod 18. Some now negative 14. I'm asking myself, If 8 were to go into negative 18, what would be, no, negative 14, what would be the remainder? So I take my calculator, 14 divided by 8, I see can go there twice. I just do it here. 18 there. Now 18 to negative 14. Go there negative 2, negative 16, subtract, and when you add, you get it. So 21a is congruent to 2 mod 8. In fact, this 21 I can also reduce it to mod 8. It's also very big. 21, 8 will go there twice. So 21 minus 15, that would be 5. It's also very big. I can write as 5. I'm going to 2 mod 8. So now I look for the inverse of 5 mod 8. The inverse of 5 mod 8, I'm using my calculator, just trying the numbers 0, 1, 2, 3, up to 7. If I try the numbers 0, 1, 2, 3, up to 7, I find that is the inverse of 5 mod 8. The inverse of 5 mod 8 is because 5 times 5 would be 25. And 8 into 25, because there are 3 terms, give it 24. The remainder is 1. So 5 is the inverse of 5. So now, multiply this equation. What was the last number? I call it 5. I call it 5. Multiply 4 by the inverse of 5, which is 5. It would be 5a is congruent to 5, 2 mod 8, and this one is 1 times 8 is a, and this is 10 mod 8, which is 2, 8. So a is 2. Now using this, I want to call it double star. Using double star, you can find x. X becomes what? 7 times a plus 6. This is 14 plus 6, which is 20. And the mod what? 6. So the answer there was 20. So therefore it's 20. 6. Get 20. Just to give a 10. It's 20. Further. 6. So that is the result of this question. That's how you do it. I want to take another example just to see whether I can use it's going to 24. Therefore, want to get the inverse of 3 mod 17. First, find the inverse of 3 mod. So you see the other previous questions, I was able to fill the inverse because the module was relatively small, but this is a bit bigger. So that means I must use extended algorithm. I must use extended algorithm for the algorithm. 17 to go there. And the remainder, this is 15, the remainder 15. What about 3? 2 go there 1. The remainder of the 1. And what about 2? 1 will go there 1. the remainder of the theorem. So this or reverse, make the GCD the subject, 3 minus 1 multiplied by 2, 3 minus 1 multiplied by, instead of 2, you write 17, 5, 4. Let me just begin from here. Okay, 1, 17, minus, what about, this is positive, also positive 5 plus this one, which is positive 6. I was looking for the inverse of 3, that I discovered is for the inverse of 3, the inverse of 3, that's right. The inverse of 3 mod 17. Yeah, that's correct, because 6 times 3 will be 18. 18 divided by 17, the remainder of the 1. So that is correct. But it was easy to see. Only that I didn't want to take a lot of time to about when I have the Euclid's algorithm. I can do that. Now, so what next? Since I've discovered that this is the inverse, I want to multiply it by equation. Multiply by equation 1 by 6. Yes. So when I do that, there is 6 congruent. Now 6 times 4 will be 24. 24 mod 17, that will be 17. That will be 7. 24 mod 17, that will be 7. Now, so what does this equation 3 mean? Equation 3, so equation 3 implies that x is the same as 17b plus 7 for some integer b. What I mean is, this equation means that 17 divided into x, you get some value I'm calling b, and the remainder of the same. That's what I'm guessing. Yes, so this is what I substitute. Well, first of all, I call it 4. And substitute 4 in 2. Substitute 4 in 2. Just get some space. Substitute 4 in 2. Just get some space, then I do that. And you see, what is the aim of this question? Because I had done a similar one, so I just wanted to now get the concept correct. Just want to get the concept correct. And again, as I said, if I'm very fast, you can always pause and listen again and then restart. Now, so I want to substitute 4 in 2 and I have 4x. But x is what? X is 17 plus 10. It's congruent to 3 mod 18. And this is just 68, I think, 68. And this other one is 28. I'm congruent to 3 mod 13. And let me take 8.8 the other side. And this will be 68 be congruent to negative 25 mod 13. But I want you to know how to divide, and you can bring it down. So I'm just asking myself, if 13 were to go from 5, what would be how many times? Because there are 13.5, negative 25, it would be 9 times. 9 times. 13 into negative 25 would be negative 9 times. Huh? 9 No, not 25. I used something different. I used 3. To be twice. To negative 2. To negative 2. Negative 2 times out with the negative 26. Then we subtract 31. 31. So instead of writing negative 25, I will write 1. What about instead of writing 68? So I'm asking myself, 13 into 68. 13 into 68. What am I right? 13 into 68. So there are 5 times. So 68 minus 5 times 13. That would be 3. So instead of writing this equation, I'll have 3, congruent to 1. And so, what I want is, I just want to find the inverse of 3. I want to get the inverse of 3 mod 13. And the inverse of 3 mod 13, looking for a number which multiply by 3 gives me, formula by 3 and divided by 13 gives me a remainder of 1. If it cannot come very fast, I can use the Euclid's algorithm. 13, 3 into 13 4 times, and the remainder is 1. So let's reverse this. So it's 1 into 1 multiplied by 13 minus 4 multiplied by 3. So the inverse of 3 there is negative 4 mod 13. Negative 4 mod 13 is the same as 9 mod 13. When you divide 13 into negative 4, the remainder will be 9. So the inverse of 3 13 is so I want to multiply this by 9, both sides. So multiply, what was this? Can I call it 5? Remember, there's an equation we want to remember. Is the question. So there's a rest right there about it. Because we want to find x. Multiply 5 by 9. On the left side, it will be b congruent to 9 mod 13. So b is 9. We want x, so we use 4. Use equation 4. We get x as 17b plus 7. And the mod is our mod. 17 times 13. 17 times 13. Our mod is 2.1. Our mod is 2.1. So what do we have inside this bracket? 17 times 9. 17 times 9 plus 7. I'm getting 160. I'm getting 160. 160 mod 2.1, and that is the answer. 160 is the correct answer. So that's how we do this question. Now Now, what about if we have three questions? If we have three questions, that's what I want to look at. And you can generalize that to if we have 4 questions. So in this case, we first find our moduli, which is this and that and this. If the moduli are relative, fine. That's how we can solve this question. The moduli are relative, pairwise relative, pairwise relative. 3 times 5 times 7. When I use my calculator, I get 1. Then now I get the moduli in respect to 3. In respect to this 3, it will be 1 of 5, or let me just say m divided by 3, which is 1 of 5 divided by 3. When I use my calculator, that gives me that. Then I also get the moduli with respect to 5. This is 5. So it will be m divided by, which is 1 of 5 divided by my calculator gives me 1. Then I get the moduli with respect to 7. This 7. If you are following what I'm doing, that will be m divided by 7, which is 1 of 5 divided by 7. That gives me. Then after that, I get the inverses of all these moduli. Like I now find inverses. Find inverses. So I find the inverse of 35. Inverse of 35 mod 5. 35 is mod 3. Mod 3. So find the inverse of 35 mod 3. But for me to do that, I first of all reduce 35 mod 3. So 35 I reduce it. 3 goes into 35. I mean, 35 divided by 5. 11 times. What will be the remainder? 35 minus 33. The remainder will be 2. So this is the same as finding the inverse of 2 mod. So finding the inverse of this is the same as finding the inverse of 3 mod. The inverse of 2 mod 3. What is the inverse of 2 mod 3? This is a very small mod. Just try 0, 1. If you try 2, it will be 4 times 2. 2 times 2 will be 10. So 3 will go there, and the remainder will be 1. So the inverse of this is 10. Now, find the inverse of this 21 mod what? Mod 5. So since 21 is bigger than 5, then reduce it. 5 into 21, 4 times, and the remainder is 1. We are finding the inverse of 1 mod 5. So find the inverse of that, because I'm finding the inverse of that. The inverse of 1 is just, also 1 times 1 is just this. Now, next, find the inverse of 15 mod what? Mod 7. Reduce 15 mod 7. Reduce 15 mod 7. 15, 7 into 15 is what? The remainder is 1. So it's the same as finding the inverse of 1. If you identify 1. Now, after you found the inverses, it's now easy. The next step is to write the result. And that's what I want to write. And I want to get this and say that therefore x is this remainder times the moduli relative to 3, which was 35, times the inverse of 35, it was 2. You see what I'm doing? This one above. And then plus this remainder times the moduli, which was relative to 5, moduli to 5 was 21, then times the inverse of 21, which was 1, plus is the remainder, which is 5, times the moduli relative to 7, was 15, then times the inverse of 15, which was 1, the whole thing mod 105. This is easy. Just multiply this with your calculator, multiply this with your calculator, multiply this with your calculator. Then add the results. When I did that, what I get, let me 2, 35, 2 plus 4, 21, 5, 15. That gives me 2 minutes. That gives me 105. I'm asking myself, if 105 were to go into 299, what would be the remainder? The remainder is 18. So this is the result. This is the result. 18. The x value. 89 is the x value. Okay, let's look at another example. This is example. We look at example 26. Example 26. It's a similar example, so we shall move very fast. Begin by finding m. M is 5 times 7 times 11. And doing on my calculator, I get it 85. You can use your calculator. What about m with respect to 5 modify 5? It would be this 385 divided by 5, and that gives me 77. What about m with respect to 7? It's 385 divided by 7. And if I do that, I get 55. What about m with respect to 10 and 11? It would be 385 divided by 11. And with my calculator, I get 45. Now, next, find inverses. Find inverses. So, what is the inverse of 77? Mod 77 is mod 5. So, first of all, I reduce 77 mod 5. 5 into 77, what is the remainder? 5 into 77, the remainder is 2. This is the same as 2 mod 5. What's the inverse of 2 mod 5? What number, when multiplied by 2, will give me a value which, when I divide by 5, the remainder will be 1. So the answer there is 10. The answer there is 10. 3 times 2 give me 6. 6 divided by 5, I get 1. So 3 is the inverse of 2, or the inverse of 7. Now, so find the inverse of 55. Mod what? Mod 7. I reduce If I divide by 7, what will be the remainder? If I divide by 7, the remainder will be 6. Let's use a calculator very fast. Now, what is the inverse of 7? No, 6 mod 7. What number when multiplied by 6 will give you inverse of, will give you 1 when you divide it by 7? That number is 6. Because 6 times 6 will be 36. 36 divided by 7 will be 35. Then we'll get that 5 somewhere. Then the remainder will be 1. So the answer will be 6. The inverse of 6 is 6. And that is the sum of the inverse of 5. Now lastly, let's find the inverse of that 5. Mod 11. Reduce that 5 mod 11. The calculator. Mine gives me 2. What number when multiplied by 2 and divided by 11 would give me a remainder of 1. Just try 0 to 10. Just try 0 to 10 and you'll find that 6 will be 1. That 6 will be that inverse. Because 6 times 12, 6 times 2 will be 12. Divided by 11, get the remainder as well. That is the inverse. So then what is x? Therefore, x, this x then becomes, this is the remainder, times the modular relative to 5 is 7, times the inverse of 7, which is 3, plus the remainder 3 times the modular which is 5, then times the remainder of 5, no, the inverse of 5 which is 6, then plus is the remainder which is 10 times the modular which is 5, then times the inverse of 5 is 6. Then the whole thing, we are doing it mod what? Mod 385. Mod 385. Now let me just do that on my calculator. 2 times 27 times 3 plus 3 times 5 times 6 plus 10 times 35 times 6 and then 35 35 mod 380. I hope you're following also with the calculator. Now that 385 into 35 52, the remainder is 87. Mod 3. So 87 is that one number which when divided by 5, the remainder is 2. And when I divide it by 7, the remainder will be 5. And when I divide it by 11, the remainder will be 10. So 85 is that one. This one is slightly different. I just draw this line directly from work out because I need to have them in the form x, x, x on the left side. That means I must multiply this, I must multiply the whole of this by the inverse of 2. I must multiply this, the whole of this by the inverse of 3. I must multiply the whole of this by the inverse of 5. Mod 11. This is mod 7. This is mod 2. What is the inverse of 2 mod 15? It's 8. Because 8 times 2 is 16. So multiply the entire equation here by 8. So 8 times x here, 8 times 2x, get x. Because 8 is the inverse of 2. Since 8 is the inverse of 2, 8 times 2 give me 1. What about 8 times 3? 8 times 3 would be 27. No, 8 times 3 would be 24. 15 into 24. The remainder would be 9. What about multiply the entire base by the inverse of the 3 mod 7? The inverse of 3 mod 7 would be what? 3 times 5 is 15. 15 divided by 7 is 1. So we have 3. So 5 is the inverse of 3. So that is by 5. So this part by 5, yes. And this part by 5 is 20. 7 into 20, 50 per remainder. Then now, what is the inverse of 5 mod 11? The inverse of 5 mod 11, just try. 11 is a very small modulus. Just try 5 times 0, 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5, 5 times 6, 5 times 7, 5 times 8, 5 times 9, 5 times 10. And usually gives you a remainder of 1. So this one gives you 0, which is not 1. This one gives you 0, which is not 1. This one gives you 5, this is not 1. This one gives you 10, this is not 1. Mod 11. This one gives you 15, 15 is 4. Mod 11, so this is not 1. This one gives you 20. 20 mod 11, that is 9. This gives you 25. 25 mod 11 is 3. Okay. 25 mod 11 is 3. This gives you 30. Mod 11, that would be 8. Huh? 30. This gives you 35. 35 mod 11, that is 2. This gives you 40. Mod 11, that is 7. This gives you 45. Mod 11, that is 1. 45. Yeah, 45 minus 44 is 1. So 9 is the inverse. 9 is the inverse of 5. This was 7. 40. 40 minus 33. So 9 is the inverse of 5. So multiply the entire equation here by 9. This would be 9 times 5x would be x. 9 times this is 63. 63 mod 11 is the same as 3 minus 55 is 8. Now, we now have equations similar to the ones we dealt with in example 20, in question 26 and 25. So from here, we now proceed the same way we did in question 24, no, question 25 and question 26. Proceeding the same. But if you have questions like the ones we have here, you must convert them in this format before you proceed. Once you converted them in this format, it becomes easy. So now find m. We're now using this because we are in what we now have what we cannot deal with. Find m, and m will be 15 times 7 times 11, and when you do that, get 1155. Then you get m with respect to 9. That will be 1055 by 9. 1155 divided by 9, which
becomes no, then it's 15. This is 15, not that's not this is 15. So 11 divided by 15, that gives me 7. Then M7, 1155 divided by 7, that gives me 165. Then M11, so 1155 divided by 11, that gives me. Now find inverses. You can do that. You'll find that the inverse of 177 mod 15. When you do that, you will find that the inverse will be 8. And the inverse of 165 mod. Now just find the inverse. I'm not, but you can reduce it fast. You reduce it fast, you find the inverse. That's the way we did for the previous questions. And so this becomes the inverse of 165, the inverse of 2. And lastly, the inverse of 105 11, that will be then you now come and find x, which will be this remainder times 105 times what? Times 77, then times 8 plus this other remainder times 165, and then times 2, and then plus this other remainder times 105, then times the inverse of 105 is 2. We are doing it more 1155, and your final answer when you do that, you get 1. That's what you get as. Now, so the only trick here is that this you must convert it in this form and then work out. And this form we've already done 2 examples, and you must be familiar now with how to do it. Let's look at the next here. Use Chinese remainder theorem to solve this. Why was I interested in this question? This question, it appears like the one in the previous, the example 27, but you consider this one as a common factor. Why does a common factor divided through by the common factor first of all? So divide this by a common factor, and that would be x equal to 3 or 7, and this would be what? X is congruent. So 2 was common here, and now 3 is common here. This would be 3 more 5. And 5 is common. 5 is common. So divided by 5, and that would be 4. So we now have what we can solve. We solve this. We now solve this using the methods we learned in example 27, question 26, and question 25. And the answer is get for x. What was I getting for x? Is just check. I have done this question. I did it, and what was I getting? Getting 388. 388. What was this? This product should be 40. This product should be 40. We just do this question. But I have already shown you that this will, first of all, divide through.
And then now solve this. You will arrive at this as the this guy, Calvin, decided to sort his CDs for sale. When he put them in piles of 5, he had 3 left. When he put them in piles of 6, he had 4 left. And when he put them in piles of 7 CDs, he had 5 left. What is the smallest number of CDs that Calvin had? So this is the question. The question is saying Calvin had, let's say let the number of CDs be X. That means Calvin has X CDs. When he arranges them in 5, he has how many left? 3 left. More than 5. So when he divides by 5, 3 are left. When he divides this series by 6, he has 4 left. When he divides by 6. And when he divides by 7, he has 5 left. So this is the question. This is the question now written mathematically. So find X. And when you do that, you will find X to be 208. Just do it using the same method we learned, for example, 25, 26, and 7, 28. And you'll find 208 as the answer. This exercise here also to ask if you understand the concept of the Chinese remainder theorem properly. Then try this exercise. Try this exercise. The answers are included. Now let's then again look at another question I've given the cut. The set of real numbers under the usual multiplication operation is not a group. Why is it not a group? It's not a group because we are member. The set of real numbers. Because the real numbers have, but 0 has no inverse. All the other numbers will have inverse. All other real numbers will have it, but 0 doesn't. But these are the properties. These are the properties satisfied by real numbers. The only that will not be satisfied is that 0 will not have inverse. Look what another question. This one was question 30. Let's look at question 31. Question 31 says, consider this group under multiplication multiply, then use multiplication table multiply to determine the following. Let's just create the under multiplication table, we don't require 0. In fact, what it will given there, the impact is not 0. So 1, 2, 3, 4, and multiplication 1, 2, 3, 4. Let's just multiply. 1 times each of these will be 1, 2, 3, 4. And the 2 times out to 2 with a 4. Remember, we are doing multiply. So 2 times 6 will be 1. And the 2 times 8, no, 2 times 4 will be 8%. Now let's multiply 3 by each of these. So 3 by 1 will be 3. And then 3 by 2. And we are doing it modifies, that will be 1. And then 3 by 3, that is 9 modifies, which is 4. And then 3 by 4 is 12 modified, it will be 2. Then let's do 4 by 1, that would be 4. 4 by 2, that would be 8, mod 5, which is 3. And then 4 by 3 is 12, mod 5, that would be 2. Then 4 by 4 is 16, mod 5, that is 1. Now, so this is the table, multiplication table, modified. Let's find the inverse of 3 using the table. So the inverse of 3 is that number which, when multiplied by 3, gives us 1. So the number which, when multiplied by 3, gives us 1 is 2. If you want, you can say mod 5. What about 2 out of 3? 2 out of 3, let's call it x. So when you cross multiply, you get 2 is 3x. So looking for number, you want to find x. So x is that number which, when multiplied by 3, gives us 2. The number which, when multiplied by 3, is 3, and this is 2. So the number which, when multiplied by 3, gives us 2 is 4. So x is 4. In other words, 2 out of 3 is 4. And then lastly, we have this. Find x if x, 4 times x is 2. This is 4. And 2 is here. So a number that is multiplied by 4 to give us 2 is 10. So x here is 10. So that's how we have to use this table to answer this question. And that's 2. That just says dash is not necessarily a property of a group. So the rest are properties of a group, but commutativity is not necessarily a property of a group. This only brought in when we're talking about an abelian group. Talk about an abelian group, that is when we now bring in the property, commutativity property. So it's not a necessary property of a group unless it's an abelian group. But the rest are necessary properties. At 3, matrix multiplication does not satisfy commutativity property, but is commutative. So matrix multiplication does not satisfy this. Does not necessarily satisfy this commutativity. Now let's look at this other example question that if B and C are elements of a group G, and if B raised to 5 and C raised to 3 are E, that means that what that means is that just let me figure this. What that means is that B raised to 5 give you the identity, and also C raised to 3 give you the identity. So find the inverse of this. Find the inverse. What we talked in class, we said that the inverse of AB, the inverse of AB will be written as BF. So you just in the change, just reverse it. So that means the inverse of this would write it beginning with the C, then B, then C, then B. That's how we write. So what is the inverse of B? No, C raised to 2. So looking for a number which when multiplied by C raised to 2 gives you C raised to 3. Because C raised to 3 is E. So for me to get C raised to 3, I need to multiply this C by C. I need to raise this, multiply this C square by C. Multiply this C square by C. Now, for me to get an E here, I need to multiply B raised to 4 by B, that I get B raised to 5. Because B raised to 5 is 6. I need to multiply this one by B. And then what about C? How do I get this one becomes C raised to 3? Because C raised to 3 is my E. So for me to make the C raised to E, to be C raised to 3, I need to multiply by C raised to 2. And then this one I need to multiply by B raised to 3.
So that this becomes the inverse. That is part C. So we write the first, we just reverse this and then write the inverse. So this is the inverse of this. So I hope you understood what we did, because for us to get the inverse of A is B if A times B gives us E. If A times B gives us E, then we say that B is the inverse of A, or we can also say that A is the inverse of B. So we want a number that I can multiply by C squared to get E. But what is E? E is C raised to 5. So that I need C. C times C squared will give me C raised to 5. Then B times B raised to 4 will give me E. And then C squared times C will give me E. And then B cubed times this B squared will give me E. So that is our answer. Which of these two are not cyclic groups? So when do we say they're cyclic groups? So if I'm given GA, now let me use supposing I have, let me use this ZA plus ZB. So these two groups are cyclic. If this is cyclic and this is cyclic, then this group, this product of groups here, will also be cyclic if A and B are relatively prime. If A and B are relatively prime, then we say that this group here is cyclic. And we already said what we mean by the word relative prime. A and B are relative prime if the only common factor between them is 1. Now, if we have more than two groups, let me say I have another Z, then I'll check the pairwise. I will consider this A and B and see if they are relative prime, or A and C, or B and C. I'll check pairwise, see whether they are pairwise relative prime. Now, so the question is, which of these are not? Now, we have no common factor between 22 and 31 apart from 1. So 1 is the only common factor. So 22 and 31 are relatively prime. So this is cyclic. 17 and 11, the only common factor is 1. So it's cyclic. This is not cyclic because 8 and 12 are not relatively prime. 8 and 12 are not relatively prime because they have another common factor 2. And again, what about this? About which is the common factor? I want to see if they have a GCD. Because if they have a GCD, then that GCD becomes the common factor. Let me see. 3, 3, 3. How many times it does? 1, 2, 2 to go there. 3, 3, 3, divided by 2, 2, 2, because they are 1. What is the remainder? 3, 3, 3, minus 2, 2, 2, the remainder is 1. So because they are 1, 2, 2, 2, the remainder is 1. What about 2, 2, 2? How many times does 1, 1, 1 go there? In fact, it was easy to see. 1, 1, 1 was a common factor. Because we go there twice. And it's 0. So 1, 1 is the BCD. This is the BCD. So these two numbers are not relatively prime because 1, 1, 1 is a common factor. So therefore, this one is not cyclic. But it is cyclic because I can see these numbers 17, 11, and 5 are all pair was relatively prime. So we've already answered that. Question 37. Question 37 says, let Z17 star be a group of units. We know what units are. Units of 17. Units of Z17. Those are elements which are relatively prime to 17. So units of 17, when you talk of units of 17, numbers which are relatively prime to 17. This is 1, 2, 3, 4, 5. In fact, 17 is prime. So all of them are units. All the elements here are units. 6, 7, all of them up to 16 are units of Z17. Because Z17 is prime, so all of them will be relative prime bits. So which of the following are generators? So this question you do it because I've been given choices. Just try and see which one will generate all these elements. Try 5, for instance. And since this is a multiplicative group, you just raising 5 to powers. So 5 to 1 would be 5. 5 square would be 25. 25 mod 17, that would be 8. Do 5, 2, and get what the value is. You will find that 5 will be a generator. So you do it up to 516. 516, so you get. You find that it's a generator. And then 8, you try 8, you find that 8 will not be a generator. 8 will not generate the elements. For this question, you already know how to find generator, how to see whether if it's an element a generator. Just try to see. 5 will be a generator. 8 will not. So that is why it's called like this. 8 will not, it's called like this. In fact, 8 and 6 are not generators. But try and see. Yes. What is the identity element in this group? This question, most people will have, they thought it would be 1, but 1 is not even a member of this group. How can an identity not be a member of the group? 1 is not. 1 is an identity element of a multiplicative group. Other multiplicative groups are not possible. An identity element. You know what the identity element does. An identity element, you add it to any element that it means it doesn't change the elements. Now, if you multiply, this is a multiplication. So you multiply that identity by that. So how would I get the identity element? There are so many ways. You can try to use let me try to use a table. Let me do multiplication table. That is the easier way, but I'll show another way. Let me use the table, and the table will help me to know which element, when multiplied by the other elements, it does not change the element. And we are doing it mod 10. We are multiplying this multiplication 2, 4, 6, 8. Just want to multiply and see which element does not change the rest. That becomes the identity element. Mod 10. 2 times 4 2 times 2 will be 4. 2 times 4 will be 8. Wait a minute, let's see. Check something. Okay. 2 times 4 is 8. 2 times 6 is 2. We are doing it mod 10. And 2 times 8, 2 times 8 is 16, which is 6 mod 10. So it's not an identity element, because when I multiply it by 2, it changes it to 8. It doesn't remain. When I multiply by 4, I get 8. I don't get 4. So it's not an identity element. Let me check 4. 4 times 2 is 8. 4 times 6, 4 times 4 is 16.
which is 6. Again, 4 is not identical because I can see when you multiply, the element does not remain. What about 6? 6 times 2 will be 12. Mod 10, that will be 2. 6 times 4 will be 24. Mod 10, that will be 4. 6 times 6 will be 36. Mod 10, that will be 6. 6 times 8 will be 48. Mod 10, that will be 8. So 6 is the identity element. 6 is the identity element. Let me try 8 and see. 8 times 2 is 16. 16 mod 10, that will be 6. Then you can see that it does not remain to 2. So 8, of course, will not be the identity. Because 8 times 4 will be 32. Mod 10 is 2. I was expecting to get 4 if it were to be identity. So the identity element is 1. And you see that a group has only one identity element. So it's this. It's 6. Let's look at this question. Choose true or false. If G is a group and the order of G is 13, then G and 1 are the only subgroup of T. That's correct. What about this? If G is a group with the order 12, then the order of every element of G is 12. That is not correct. That's not correct. Because G has order 12. Then the order of every element of G is 12. That is not correct. Because the order of an element of G will be given by the order of G is 12, divided by the GCD. The GCD of the order, the GCD. Now, supposing the element is 3, supposing you have element 3, then it will be the GCD of 3 and 12. GCD of 3 and 12. What about if it's 6? GCD of 6 and 12. Okay. If G is a subgroup of G, if G is a subgroup of G with the order of G being 15 and the order of H, this is the possibility. Okay. This is the possibility. So that we say, if H is subgroup of G and the order of G is 12 and the order of 3 is H is 3, then every coset H has 5 elements. That is not correct. Because the number of elements of the coset should be the same as the order of the sub. The same as the order of the sub. Not 5. Why do you take it 5? I'm taking this letter by that. No, that's not correct. Okay, let's look at this. This is another good question. Assume that G is a finite group with a subgroup of H. Subgroups H and of order 12 and G is let this be clear. Let this be clear. So let me read the question. Assume that G is a finite group with the subgroups H of order 12 and K of order 30. So you have two subgroups, one order 12, another one order 30. If the order of G is less than 200, what are the possible values for the order of G? And I've said that use Lagrange's theorem. What does Lagrange's theorem say? It says that the order of a subgroup must divide the order of the group. And now we have two subgroups. So the easiest way to do this, since we have two subgroups, to get the GCD of their order.
the GCD of their orders is 12 and 30. And so that GCD must divide the order of the group. So the GCD is therefore, if it would have been one group, it would have been one subgroup. The order must divide. The order must. So we can tell that if it was only H, we could tell the order of G, because the order of G should be numbers that itself can divide. 11, 12, 11, 24, 11, 48, and so on. But now we have two groups, and we want the likely orders of G. 2 would go here 6 times and 15 times. 2 would go here 3 times and 5 times. 3 would go here once, and 5 will go here once. So the GCD of these orders is 2 times 2, which is 4, times 5, equals 20 times 30, 60. So the possible orders of G there is 60, and another number that the 60 can divide is 120. Another number that the 60 can divide is 180. And we wanted it to be less than 1. So those are the possible orders of G. So G is possibly of order 60, of order 120, of order 180. So that this order can divide. The order of H must divide the order of G, and the order of K must also divide the order of G. These two orders must divide the order of G. So the possibility for the order of G therefore is 60. So that both 12 and 30 can divide, it must be 60. Another order that both 12 and 30 can divide is 120. Another order of G that both 12 and 30 will divide is 180. Those are the possibilities of the order. That's what the question wanted. Let this be sigma be this. Is this sigma even order or odd? So for you to tell whether it's even or odd, first of all, it's easier to write it. The product of circles, and then after that, write it as a product of transpositions and find out how many transpositions there. So how is it in cycle form? So sigma in cycle form would be 1. 1 goes to 3, and 3 goes to 7, and 7 goes to 1. So it goes, because 7 has 1. We now write what is not here. The next number that is not here is 2. 2 goes to 8. 8 goes to 5. Is 5. 5 goes to 4. 4 goes to 2. So we already have a 2, so it goes. What is missing here? We have 1, 2, 3, 4, 5. 6 is not there, so put it there. 6 goes to 9. 9 goes to 6. It goes, so it goes here. Now, so how many transpositions are here? This first cycle has 2 transpositions. 1, 2. Or remember, we said that if it has odd number, then it will have will be even. It will have the number of transpositions are n minus 1. N minus 1, where n is the number of entries. The entries here 1, 2, 3. So 3 minus 1 gives you the number of transpositions. I want to multiply it up to write as a product of transposition because that was other question. And how many transpositions do we have here? 1, n is 1, 2, 3, 4. So there will be 3 transpositions, n minus 1. And how many transpositions will be here? 1, 2, that will be only 1 position.
So 2 plus that is 5, that is 6. So this would be 6 transpositions. So if you have an even number of transpositions, then we say that that permutation there is even. And if you have an odd number of transpositions, then we say that it is odd. In this case, you have 6. So 6 is even, therefore it's an even permutation. What is the order of this? The order of this, you get the order of the first cycle, and the order of the second cycle, and the order of the third cycle, and then the BCD. So you build the BCD of the order of the first cycle, 1, 2, 3. The order of the second cycle, 1, 2, 3, 4. And the order, no, not the BCD, should be the LCM. The LCM. Should be the LCM. And this other one is of order 2. What is the LCM? 3, 4, 2. 2 goes here. 3, 2, 1. 2 goes here. 3, 1, 1. And finally 3 goes here. 1. So 4 times 3, which is 12, is the order. 12 is the order. So it's the LCM of the orders of the cycles. If G is generated by A, is a cyclic group of order 100, what is the order of A raised to 5? So as we had already said, the order of an element A raised to 4 would be the same as the order of the group divided by the BCD of 24. What is that BCD? That BCD is 100 over 4. That order is 24. So the order of this is 24. What about the order of this direct product group? The order of that will just be the order of the first group, which is 40, and the order of the second group, which is 60, and that would be 1. So that's how you're supposed to have done that. Now, this other question, consider the cyclic group, this cyclic group of order 4,900. Give the number of generators. The number of generators. How many generators? So the question is not asking for us to list the generators, but to say how many generators there are. So first of all, we find out this number as a product of the prime factors. So 4,900. How many times does 2 go there? Let me just use my calculator. 4,900 divided by 2, that gives us 2450. What about 2 there into 2450? Because there are 1225 times. 1225 times. I think 3 can go here. This is 3 plus 7. 3 not. Use 5. Then we use 5. 5 will go there. So divided by 5, I have 245 times 5 can still go there. So divided by 5 again, and 49. And then 7 will go there. So there are 7 times. Then 7 goes there once. So 4900 can be written as 2 raised to 4, or 2 raised to 2, times 5 raised to 2, times 7 raised to 2. So the prime numbers, the prime factors of that of this 49 are just 2, 5, 7. So how do we get the number of generators there? Number of generators
are given by 1 minus a half. That a half is coming from this 1, this 2. Then times 1 minus a fifth. This fifth, this 5 is this. Then times 1 out, 1 minus 1 out of 7. This 7 is here. Then times 49 is here. So this would be a half times 4 out of 5 times 6 out of 5. No, 6 out of 7. 6 out of 7 times 49 is 0. And this, if you use a calculator, this should give you 1680. 1680 generators. 1680 generators. So that's how you find the number of generators. And so you just find, first of all, that how many prime factors do we have. And so 1 minus 1 out of the first prime factor, then times 1 minus 1 out of the second prime factor. And this is there. And then times that 1, and so on, depending on the number of prime factors. Suppose, this question for first, suppose G is a group defined by this Fermi table. Okay. The centralizer of 5 is in G is this. The centralizer is 1, 2, this set comprises 1, 2, 3, 4, 5, 6, 7, 8. True or false? So what is a centralizer? The centralizer is the set of elements. The centralizer of 5 will be the set of elements that commute with the set of elements that commute with 5. We just come here and check what elements commute with 5. Which elements commute with 5? Just check. 1 times 5. 1 times 5. You can see is 5. What about 5 times 1? 5 times 1. Then you can see 5 times 1 is 5. That is 5 times 1. What about 1 times 5? No, 2 times 5. 2 times 5. You can see it's 6. What about 5 times 2? Is it also 6? 5 times 2, you can see it's also 6. So that means 5 commutes to the 2. What about 3 times 5? 3 times 5. 3 times 5, I can see it's 7. What about 5 times 3? 5 times 3, I can see it's also 7. So when you do that for all the elements, you will find that what has been given there is the centralizer. So the centralizer are all the elements that commute with the 5. So the elements that commute with the 5, all of them are 1. 1 has commuted with the 5. 2 commutes with the 5. You've seen that. 3 commutes with 5, and so on. So the elements given in that question, all of them commuted. Just check and see. So the answer was true. So the answer here is true. Now the other one, the centralizer of 3 is this. Let's just check. Let's just check and see what the centralizer of 3 is. Want to see what element to commute with 3. That's what it comes from the centralizer. So 1 times 3 is 3. 1 times 3 is 3. What about 3 times 2? 3 times 1. Times 1 is 3. So 1 commutes with 3. What about 2 times 3? 2 times 3 is 8. What about 3 times 2? 3 times 2 is 4. 3 times 2 is 4. So 2 does not commute with the 3. What about 3 with itself? 3 times 3, of course it will commute. 3 times 3 is 5. What about that 55? So 3 commutes with itself. 3 commutes with itself. So we found one member of the centralizer here. And what about 3 times 4? 3 times 4 is 6. What about 4 times 3? 4 times 3 is 3. 4 times 3 is 3. So 4 does not commute with 3. What about 5? 5 times 3. 5 times 3, already we have seen that we commute. 5 times 3 is 1. No. 5 times 3 is 7. 5 times 3 is 7. What about 3 times 5? 3 times 5, 3 times 5 is 7. So 5 commutes. Let's check 6. 6 times 3. 6 times 3 is 4. What about 3 times 6? 3 times 6 is 8. 8. So 6 does not. What about 7 times 3? 7 times 3 is 1. What about 3 times 7? 3 times 7 is 1. The 7. We are left with 8. Let's try 8. 8 times 3. 8 times 3 is 6. What about 3 times 8? 3 times 8 is 2. So 8 does not count. So the centralizer of 3, with respect to G, are the elements which commute with that, which is 1, and we've seen 3 itself. We've seen this was 5, and we've seen 7. And so that is what the question has given us. That means it's true what has been given, the centralizer of 3. As you see, we found the given 1, 2. If I captured correctly, what did we found? We found was 2 centralizer. I had found 3, 7. Those are 5. I think those are 5. This question is supposed to be 1, 3, 5, 7. These are the centralizers. Yeah, these are the centralizers. I think, but in my cut, this was given as correctly this way. So the answer is supposed to be true. But if it remains like this, then the answer will be false. Now, the center of a group, those are elements that commute with every element. The elements that commute with every element. We found 1 commutes with every element. We found that 5 commutes with every element. And then we want to test and see which others commute. So when we use this this question, we've already been given that 3 only commutes with this. 3 only commutes with this. So that means we cannot test if 8 commutes with every element because it has not commuted with 3. So we cannot test. We cannot even test 6 because it's wasting time if we test to check if 6 commutes with every element. Because this question has already told us that the only elements that commute with 3, in fact, are these ones. 1, 3, 5, 7. And 5 already commutes with every element. So it will be in the center.
So the center has 1, has 5. We are looking for another element to add in the center. 2 does not commute with every element because it is not commuted with 3. It not. 4 did not commute with 3, so it does not commute with every element. 6 did not commute with 3, so it does not commute with every element. 8 did not commute with 3, so it does not commute with every element. Yeah, those are now the only elements we need to test whether it commutes with every element is 7, because it did commute with the 5. It has commuted with the 3, so we need to see whether it commutes with the other element. If it commutes with the element, then it will qualify to be the center. Let's just check and see whether it commutes with the element. 7. We are testing to see whether 7 commutes with the element. And of course, 2 does not commute with 3, because when we checked 2 times 3, we found it to be 8. And when we checked 3 times 2, we found it to be 4. So 2 does not commute with 4. So that question there, I ought to wrongly, it was supposed to be 5. Now, so we just want to check whether 7 commutes with the element. Of course, it will commute with 1. Let me check 2. 7 times 2, 2 times 7 is 4. What about 7 times 2? It's 8. So 7 does not commute with the other element, so we don't need to proceed. Check the other elements. So that means that 7 will not be in the center. We had disqualified 2 as not being in the center because it did not commute with 3. Because this is not correct. This is supposed to be 1, 3, 5. So we disqualified it. So the center has 1. The center has 1 and 5. We disqualified 4 because 4 did not commute with 3. I didn't want to check other elements that it does not commute with. But since it did not commute with 3, it does not commute with the other element, and therefore can never qualify to be the center. 6 also did not commute with the 3, and therefore does not qualify to be the center. 7 has not commuted with the 2. We just tried that, and so it does not qualify to be in the center because an element that is to be in the center is the one that commutes with every element. 8 did not commute with the 3 here, so it does not qualify to be the center. Now, let's come to this question. D. Use the above table to find the order of 2, 3, 5, and 7. The order of 2, 3, 5, and 7. Let's just go back to use the table. Of course, you can never do this question without the table. Order of 2 and 3, 5 and 7. That's all the question. We just write it here so we should not be going back. We require the order of 2, 3, 5, and 7. Now let's begin with the order of 2. One that element which, when raised to 2, you get the identity. First of all, what is the identity element? The identity element here is 1. The identity element is 1 because 1 times 1 happens to be 1 times 4 is 3, 1 times 4 is 1 times 5 is 5, and so on. So 1 is the identity. So 2 raised to 1, what does it give? Okay, let me just begin with the 2. This will just be 2 on it. But 2 raised to 1 is just 2. What about 2 raised to 2? Which is them are 2 times 2. 2 times 2. That gives me 1. That means the order of 2 is 2. This part. The order of A is n if A raised to n gives me the identity. So the order of 2 is 2. Let me check the order of 3. 3 raised to 1, 3 raised to 1 is just 3. What about 3 raised to 2? This is 3 times 3. 3 raised to 2, 3 times 3. What about 3 raised to 3 raised to 3? 3 raised to 3 is the same as 3 raised to 2 plus 1, which is 3 raised to 2 times 3 raised to 1. But 3 raised to 2 is 5, and 3 raised to 1 is 3. So what is 5 times 3? 5 times 3 is 7. So that means 3 raised to 3 is 7. We want to check 3 raised to 4. 3 raised to 4 would be 3 raised to 3 plus 1, which is 3 raised to 3 times 3 raised to 1. But 3 raised to 3 is 7. And 3 raised to 1, 3 raised to 1 is 3. So this is 7 times 3. 7 times 3, which is 1. 7 times 3 is 1. 7 times 3 is 1. That means the order of 3 is 4. Because 3 raised to 4 gives us 1. I hope you got that. Let me do 2 more. 5 and 7. If you never got the first 3, you get this one. If you never got the first 3, then you have a chance to get what I'm doing. I want to get the order of 5. So I'm looking for a number which, when raised to 5, gives me the identity. The identity is 1. So 5 raised to 1, just 5. What about 5 raised to 2? That is 5 times 5. 5 times 5. It is of course 1. This 1. 5 raised to 2. It's 5 times 5. So the order of 5, therefore, is 2. Because it's this power that has given us 1. Let's check the order of 7. 7 raised to 1 is just 7. 7 raised to 2 is 7 times 7. 7 times 7, it is 5. 7 raised to 3 is 7 squared times 7, which is, but 7 squared is 5. Then this other one is just 7, which is 5 times 7. So 5 times 7 is. What about 7 raised to 4? So we go until we find the identity 1. This is 7 cubed times 7. But 7 cubed is 3. 1 times 7. 3 times 7 is 1. So that means that the order of 7, the order of 7 is 4. That is how you're supposed to have done that question. During calling, I keep this question I didn't put. So which of the following are multiplicative tables for groups with 4 elements? So I want to see which of these tables will form a group of 4 elements. So for it to form a group we want to see whether there is closure. Of course, there's closure for each of them. Because I have elements A, B, C, D. I'm just seeing A, B, C, D, all of them, not seeing anything. So you don't need to check that, because closure, you can easily see that every time you did multiply, you got A, B, C, D, A, B, C, D. No foreign element is coming up. Associativity is checked. So we just want to check if the group has identity. If it has identity elements, and then we shall check if every element has a universe. Identity element, let's get 2. So an element will be identity if I multiply A, I get A, multiply B, I get B, multiply C, I get C, multiply D, I get. But this, in fact, this one has A is identity element. Because A times A gives me A. A times B gives me A times B gives me C. A times D gives me. So A is the identity element. So when I assume that A is the identity element, then I want to see if every element has an inverse. That's what I now want to see. Every element has an inverse. So the inverse of n shall be m if n times n gives me the identity. So let me see. Like B, the inverse of B is B. The inverse of C is C. And the inverse of D is B. The inverse of B, the inverse of B. So I think this forms a group. This first step we are from because it has identity element A, and every element has an inverse. I can see the inverse of A. The inverse of A is A because it's the other element that if I multiply by their each, I get the identity. So if I multiply A times A, I get the identity which is A. If I multiply B times D, I get the identity which is A. So the inverse of B is D. What is it that if I multiply C, I get the identity? C times C gives the identity. So the inverse of C is C. What about D? The inverse of D is D. Because D times D gives the identity. So this first one is from something. Let's check the second. This one. Let me see the identity element. A is the identity element again because A times A gives me A times B gives me B, A times C gives me C, A times D gives me D. Let me check if every element has an inverse. What is the inverse of A? The inverse of A, an element that I should multiply A to get the identity, that element is A. What about the inverse of B? B times B gives me A. So the inverse of B. What about the inverse of C? The inverse of C, the inverse of C is an element can never have two inverses. This question is saying that the inverse of C is C and at the same time is D. The inverse of an element is supposed to be unique. So C can never have two inverses. So that disqualifies this from being a group. You cannot have one element with the two inverses. So C, when C has an inverse to D, then an inverse to D. That is not possible. The inverse is supposed to be unique. Let's come. So this is not a group. A was a group. B is not. This is not. Let's get this. What's the identity? The identity again is A. So it's always easier if you identify the identity first of all. Because A times A gives me A times B gives me B, A times C gives me C, A times D gives me D. So A is the identity. Let me find the inverse of A. An element that multiplied by A give me A is A, so the inverse of A is A. What about the inverse of B? Is B. The inverse of B. B times B gives me A, that is okay. The inverse of C. C again has no inverse. C has no inverse in fact. There's no element which you can multiply by C to get the identity A. C has no inverse. So that disqualifies this from being. So again, this is not a. C has no inverse. You can see C times A gave me C and C times D gave me C. So C has no inverse. So that is how you're supposed to have done this. That is the end of today's revision questions. Hope you've learned something.
If you have forgotten something, you've been reminded what it is. So it means that you need to do as many examples as possible. Thanks. For those who have not subscribed to my channel, remember to subscribe so that whenever I upload more other videos, you can automatically receive